Hi, welcome to the session of speed control of DC series motor. In this method, we can discuss on the methods available to control the speed of series series DC motor. First is a flux control. So under flux control, we have different methods. First one, that is field diverter method. In this method, this is the symbolic arrangement made for the field diverter method, where I need to divert the field of this series by connecting another resistance, that is Rx. So the series field winding is shunted by an inductively wound diverter resistor. Why inductively wound diverter resistor? Because it will avoid oscillations in speed initiated by the load changes, as shown in the figure. Its speed current characteristics, if you look at it, it is decreasing. So if you look at as Ia increases, the speed is decreasing. So by adjusting the value of this Rx, at any amount of current can be diverted through the diverter. So hence the current through the field winding can be adjusted as per the requirement. Due to this, the flux gets controlled and hence the speed of the motor gets controlled above the rated value. So the next flux control, we have another method, that is armature diverter method. So here if you look at it, the armature current is made to divert by connecting an resistance, that is Rx. So in this method is used for the motor which requires constant load torque. So the armature of the motor is shunted with an external variable resistance Rx, as shown in the figure. So any amount of armature current can be diverted through this diverter, by adjusting this diverter value, thereby armature current reduces. So if you have a less resistance here, the armature current is more here, and if you have more resistance here, if you have a less resistance here, more current flows through this diverter and less current flows in the armature. Therefore, we also know that T is proportional to phi Ia. So as the load torque is constant, the flux is to be increased, and therefore motor draws more current from the supply with increase in the current through the field winding. So flux increases and speed of the motor reduces. As we know, the speed is inversely proportional to the flux. So this method is used to control the speed below the normal speed. So next, the third flux control is the tapped field method. In this method, the field ampere turns are adjusted in steps. If you look at it, we have 1 step, 2 step, 3 step, 4 step and 5 steps. So it has been divided into 5 steps of this resistances, the number of turns. So as shown in the figure. So the selector switch, the selector switch S is provided to select the number of turns as per the requirement. Okay, if it is in the position 1, the entire field is in the circuit and the motor runs with normal speed. As switch is moved from position 1 to 2 and onwards, the number of turns of the field winding in the circuit is decreased. Due to this, the flux produced also decreases, thereby increasing in the speed of the motor will be above the rated value, and this method is often used in electric traction. So the next method under flux control is series parallel connection of field. If you look at it, the series method, which is given by the circuit A, and the parallel connection which is given by the circuit B. In this method, the field is divided into various parts. So these parts can be connected in series as shown in figure A or in parallel as shown in figure B. For the same torque, if the field coil is arranged in series or parallel, MMF produced by the coil changes, hence the flux produced also changes, and thereby speed can be controlled. Some fixed speeds only can be obtained by this method. In parallel grouping, the MMF produced decreases and higher speed can be obtained and is generally used in case of fan motors. So the next method of speed control of series motor is rheostatic control, that is armature voltage control. So the circuit is shown as in the figure. So in this method, the variable resistance Rx is in series with the armature, and the applied voltage is varied as shown in the figure. So, and also see the characteristics of the speed and current. So, as the resistance is inserted, the voltage drop across the resistance, this resistance IARX occurs. This will reduce the voltage across this armature. So as speed is directly proportional to the voltage across the armature, the speed reduces. So also the entire current passes through the RX. There is large power loss because of this. So because of certain limitations, only speed below the normal value can be obtained. If you look at, this is the rated speed, and below the normal value can be obtained by increasing in the Rx value. So range of speed available is limited because efficiency is reduced drastically for large speed reduction. So the speed regulation is poor as for a fixed values of series armature resistance. The speed varies directly with the load, being independent upon the resistance voltage drop. So generally this is economically feasible only for very small motors, that is fractional of kilowatt. For short time, intermittent slowdown for medium sized motors. The last method we have here is the applied voltage control method. So in this method, the series motor is excited by the voltage obtained by a series generator as shown in the figure. So if this motor field is excited by this generator connected. So the generator is driven this generator is driven by a suitable prime mover, so that the voltage obtained from the generator is controlled by this field diverter resistance connected across this series field winding of the generator. So as a result, eg the EMF is directly proportional to the flux. The flux change is achieved gives the variable voltage across this. So at the output terminal of the generator, so due to the change in the supply voltage, the various speeds of DC series motor can be obtained. Thank you for watching.